Hello and welcome back. So this is another stream in the ongoing implementation of Lambdas in my Feersum scheme compiler. So I'll start by going over what we did in the last stream, and then we can have a look at what we're going to do today. Most of the work in the last stream was to do with compiling the packing and unpacking of arguments from calls. So when we emit a lambda definition, we use this emit named lambda to write out the actual body, and we split it into two separate things: a method that has the parameters that the lambda you would expect the lambda to have, and we have a second method which we're calling the thunk, which is what we use to create our lambda object that we pass around as a value. And then we have what we call this unified calling convention. So whenever you call a lambda, the function type in .NET is a func of object array to object. And then what happens is when you apply a function in Scheme, we pack all of the arguments up into an array, call that thunk, and then the thunk's job is to unpack the arguments and turn them back into something that we can pass into the real lambda's body. So the problem we got was at the end of the last stream, we got to the point where that worked fine as long as you provided the right number of arguments for the function. But there's two kinds of functions in Scheme. One has like a set number of arguments that must match a pattern, and another one you can have a pattern and then a rest parameter, which is then set to an array that contains any other parameters that are provided. So if we have a look at how that works, we've got this fix me comment, which is where we need to start work on this stream. So in our thunk, we call this unpack remainder, telling it the index to start at, and then it's its job to take everything after that in the array of parameters, pack it all up into a scheme list, and use that as the value. But the current implementation of that is just this stub that loads null. So what's happening is, if we define a function that takes a variable number of arguments, it will always receive null, or the empty list, as that argument type. So I can show that by actually running the current implementation. We go and type in a function definition, so we can define a lambda as lambda x dot y, and this lambda will accept at least one parameter, but maybe it would have more than one parameter. If we actually try and call that lambda and say we give it two parameters, and you'd expect, if things were working correctly, so that's not calling, is it? We say y, and then if we call it with two parameters, you'd expect this to return the second parameter, or a list containing the second parameter, but that's not what's happening because we're not properly unpacking it. So where we need to start here is lists in Scheme are implemented as what are called cons pairs. So they're linked lists. So a list is just a pair where the right hand side or the tail of the list is another list, or the right hand side of the pair is a list. It's a list. Or if the right hand side is null, because null and the empty list are synonymous in Scheme. So the plan is that we first need to come up with a type to represent a cons pair. Now, one option would be to use some existing built-in .NET type. Like we could represent a pair as just an object array that contains two things, or we could also represent it as a custom type. I'm kind of tempted to represent it as a custom type. So we'll do some work in the compiler to support this. So when we emit, we create an assembly definition. This is a mono.cecil assembly, and we add our module to that. We add a type for our program. I think we could probably have another method here that goes in and adds the type for our cons pair. So let's create a add core decl's method, which will take the assembly, and I'm not sure what it will return yet, so we'll see. We'll just see what happens there. That takes an assembly, which I think we are going to want to annotate, maybe type annotation here. Yeah, so the compiler can't quite work out yet what the assembly is, so we'll add a type annotation for that. Then we need to work out what we're going to do in here. So we can start out by, we're going to want a class definition, because cons pairs are going to want to live on the heap, so they've got to be reference types, not value types. So if we make the cons tie, we can give it the name is going to be cons pair. Is that the right type definition? No, namespace is going to be, we'll call it well, what does .NET call it? We have Microsoft.C#. We have like system.runtime.compiler services. So maybe Feersum.compiler services would do as a compiler namespace. Let's extract that into a variable that we can use. That is capitalized badly. There we go. The type is going to be cons pair. It's going to be a public class. That seems good so far. I'm going to want to add create an empty constructor for in this assembly and add it as add it as a constructor on this, which you just do by adding it as a method. All right. So now we should have an empty class, and let's run that and check that it works. So if I run the compiler with .NET Run, pass it one of our specs. So let's just do strings scheme. Oh yes, we need to give it the project. So if we do this, we can then do il spy -d spec strings.exe to see. Oh no, it's just il spy -il. Yes, so we can see the il that was generated by our compiler. So we've got the main method, we've got the script body, which in this case just loads a few strings. It doesn't do anything interesting. We've got, that's our Lisp program. And we haven't added the cons type to it. So let's go and do that. So we need to do assembly types? Well, no. Oh, yes, main module types add. So now we will write out that type. Takes a while to run our compiler when you have to run another compiler to generate it in the first place. So what do we get now? We have the cons pair class emitted with an empty constructor that just calls the parent constructor. Good. So a pair in Scheme is made up of two values, so we're going to want two fields. Now, because these are forming a list, you could think that the left-hand value should be an object because we can store anything schemey in there, and the right-hand should be a cons pair again. But you can use pairs for things that aren't lists, like you could just put two numbers together. So I think what we're going to actually want is two properties, two fields. There's no need to make them properties, just two fields, and they're both going to be object fields because this is Scheme and types are at runtime, so everything's an object. So const dot fields dot add, and I think we can just do field definition. A field definition has a name, so the left hand item in a pair is called the car for reasons. Field attributes dot public So we just want it to be public, and the type is going to be the main module type system.object. What is this upset about? Field definition. Does that need that? Yeah. Because otherwise we have to call it explicitly. So we also want a right hand field which is called the coulda for equally good reasons. So now if we run this again and then inspect the output, we should see that we have a cons pair type that we can use to build a list. And if we look at the IL, we have two fields, both of them objects. So what we're going to want here is something to return from the core declarations to be able to store that cons type on. And then we can put it into the emit context. Because we could look this type back up from the assembly type system again, each type, but we've already got the program type, so we can put the cons type in there next to it. I'll store the cons type there, and then we'll return it here. And we need to add the cons type to our emit context definition. Let's refactor this. This is looking a bit. What was I? I was clearly in a different mood when I added all of these semicolons. Still not 100% sure which way around people tend to prefer them in F#, but I've seen people in is it Elm tend to put them like this, and I was initially quite against it, but it does grow on you. So we've got the cons tie here when we create the named lambda, and we're creating a can we do ... or something like that to copy the rest from the context. Can we do a copy rest when we create a record and update record expressions. That sounds like what we want. It says record name with updated labels. Records are immutable by default, so you can do record2 with y equals. Fair enough. So this, we're getting a new IL processor here, but what else? We keep with context with a new IL processor. And program type is copied across. Next lambda is 0. Copy and update record expressions. So this is saying that you do updated labels like that. Y is, so assuming y equals 100, z equals 2, so it's just, I'm confused as to why that is. Just says unmatched. Scoop prefix is going to be new assembly, like that. Unmatched. Unexpected. I wonder if does this need more brackets? Found our first sidetrack of the day. Maybe if we do that, things will be just reorder things a little bit. Expected symbol and expression. This is going to be because this is not indented enough, maybe. Can't see where that's going wrong. But if I put it on one line, it'll just suddenly magically work. That works, so I'll leave it like that. It's always indentation. And then we should have access to that cons type. So instead of emitting a load null, I think the first thing we want to do is we'd call, so here we know, let's think. So how much of this do we know at compile time? We don't know the size of the arguments array. So if we do unpack arg, if we do let's just do an example so I've got something to talk about here. So what I'm thinking about here is when we call unpack argument, I don't think we check whether or not we actually have an argument at that index. So I bet if I do something like this, I'm just going to use define because it's easier to define a function. If I do define, well, let's do that again. No. Let's do the run again. If I define a function like lambda, which takes two values and returns the second one, and then I call it with one value, we get an exception. What is the exception? Let's print it out here in the debug console because it can be made bigger. So the exception is a target invocation exception, and inside it, it has index out of range exception. So the problem here is that we don't actually check that that index exists before we try and use it. So we kind of won't want to know in a few places we're going to want to do an index check. So I think when we've got a simple list, we don't care how big the array is. We're just going to build up a list. When we've got a fixed number of arguments, what we should do is really check that the array is actually the same size. So what I'm going to do is I'm going to start up another scheme implementation, and I'm going to see what happens when we try and do the same thing in this scheme. So if I do a lambda that takes two parameters, returns the second parameter, and I call it with one parameter, get bad argument count, like received 1 but expected 2, and it's being thrown at the eval of that lambda, so it's at runtime. Right, all good. So I think we're going to want to do the same thing here. So we know how many arguments we're expecting as formals. Is the formals so I think what we could do here is what we really want to do is throw an exception through in the thunk. If the size of the first of the array is not exactly the same. So we'll do, first thing we want to do is load the array. So if we load the array onto the stack, and then we want to get the array length. Is there a how do we get the length of the array? Let's try. So if we just do, if you have a method which takes an object array and returns an int, what does it compile down to? It compiles down to load len. Right, I thought there was an opcode for it. So if we load the length, then we're going to I'm going to do a comparison. So we want a branch. There's a branch if equal, branch if less than equal. So if we've got branch if not equal, what is this? If you have a look at the opcodes class, it usually has the list of all of the opcodes. So if you've got branch not equal we're going to push the constant onto the stack and then so if you load a constant of expected argument count, we will what we'll do is we'll have an error handler that just throws a generic exception for the time being. And we'll just say like argument count mismatch or something. Just let. I'm just gonna somewhere in here we do a not. Yeah, I'll create. So we create an opcode. We create an instruction. So basically the way that jumping works in mono.cecil is that you create this instruction. In this one I'm going to do, yeah, we'll call it error. So you create an instruction. In this case I'm just going to use a NOP instruction. And then when you want to, actually I need to omit that in the thunk. So we create an instruction. I've spelled thunk terribly there. You create an instruction. You can use that as a jump target at some point. So everything will be going fine. We do this argument check, and if the argument count it doesn't match, then we do that jump. And then later on down here, we will emit the actual argument check. So we do that by emitting the instruction we kept stored at the top. And then we need to emit a return instruction. So we emit an opcode, or is this is an instruction. Check again at that if. So when we emitted the if, we did the same idea, but effectively the idea behind this is that you create an instruction and that there you call append instead of emit. So you create the instruction ahead of time and then add it manually into into the IL stream, and then the jump targets will be kind of patched up afterwards for you. And we're at the end we're using this body optimize, so we'll just use these normal branch instructions, and then the body optimize will just sort out dealing with things like what happens if you could do a short branch to that and things like that. So mono.cecil is quite nice from that point of view, that we don't have to worry about it. And it might appear kind of wasteful to have this NOP instruction, and it will slightly bloat the size of the code, but you can do peephole optimizations and that kind of stuff later, and the JIT's going to get rid of the NOPs. They do sometimes come in useful for things like debugging, like you might find that you have a NOP lying around anyway. So all is good, and in some cases you would know what the instruction was that you were going to emit. So in this case we will do well, actually here is a trick. If you do opcodes load null, so if you load a null and then we emit an opcodes dot throw, and then return, what that should do is it should mean that instead of getting an argument count exception, we should now get a null reference exception when we try that broken piece of scheme code. So this is a shorthand way of throwing a null reference exception. effectively what you do is you ask the .NET VM to throw an exception, and then it immediately tries to use that exception, but it's null, kind of. So xy, return y, call it with one argument, pause on exception again. If we go to the debug console, the exception is a target invocation exception, and the inner exception is a null reference exception from the Lambda thunk. So what we need to do here is we could probably come up with a method for raising an error with a specific string, but let's do this here for now, and then we can abstract it later when we know what we want to do. So instead of the load null, we'll do a load constant string. Load string. We can actually even say how many arguments we were expecting. So we know it is expected argument count. Oh no, No, we'll leave it that for the time being. Then what we need to do is create an instance of the exception type. So we do opcodes.new object. We need to give it the constructor for exception, so we'll import that. So we do assembly because to be able to use the constructor for exception, we need to we need to have a reference to it first. So we can do type of exception dot, and we want the constructor has VS Code crashed there. Kind of looks an awful lot like it has. Yeah, reopen it, please. So we want the constructor that takes a string. Okay. what has gone wrong there? We're changing the value. We're changing the return value of a named lambda by accident here. I think it should fix itself in a bit. It's because we've got too many closing everythings, I think. For some reason, code seems a little bit overzealous with adding pairing brackets and things. This is complaining about. So this still thinks that that is an argument. That works. So hopefully this should now create a system exception that says argument count mismatch. Unless I've completely forgotten something. We have a lambda that takes 2 parameters, change the second one, call it with 1 parameter. We get an exception, and the exception says argument count mismatch. Good. So that's working. I'm going to commit that for the time being. We got the cons type stuff. No, we'll leave it then, we'll leave it. We can commit it all in once later. So if we've got a dotted list, then the expected argument count is going to be the same. It's going to be the length of the formals there. But instead of branching, this says branch if not equal. We'll now do branch if less than. So if we have fewer arguments than we're expecting, and then we will, so let's just check that that works. The idea being here that we don't actually mind if you provide more arguments, because you've got that rest parameter that you can put the rest of the arguments into. Thinking that this sequence of instructions is, well, see, it's only 2 instructions long. This sequence of instructions, is that worth getting into a is that worth being in a method? Maybe. We have a lambda that takes 2 parameters, and we call it, and we want a lambda that takes 2 parameters, where one of them is optional, and we want to call it with 1 parameter. That should be fine. It is. I have a lambda that takes 2 parameters, turns the second parameter, and we call it with only 1 parameter, with no parameters. That should not be fine. We should get argument count mismatch. do get an argument count mismatch. Good. Then the other thing to prove here is we can not call a lambda with too many parameters. So say we have a lambda that expects one parameter, and then we call it with 2, 3, whatever parameters. We also get an argument count mismatch. Let's get the new exception out straight away. There you go, argument count mismatch. So we're doing the check for the fixed part. Then the unpack remainder, it's its job to work out which index we want to start at and then build up the list. What we ideally want at the end on the stack is the list's head. So the logical way to go around this is not actually to loop through. So if we imagine that there's this list of parameters that says like 1, 2, 3, I'll put this in a comment so that, yeah. The logical way to do this is if you imagine that you're then applying that to something that looks like this, x dot y, the first thing you do is you walk through, you take the first parameter and bind it to x, and then we've got the index should be for 2 and 3. So the index is going to be 1 that we've managed to get up to. And then we want to have a list that contains 2 and 3 on the stack. So the best way to do that is to start off with 3 and put that in a cons pair, and then so we would end up with a pair that looks like 3 dot the empty list, and then we would have that on the top of the stack, and then we would take another pair which is like 2 and then that previous value. So the first thing to do, we're going to need to emit some kind of loop here. So I think the first thing we're going to want is another NOP code. Do we need that? Because the loop's going to look something like get length of array, and then it's going to be store it as a local, and then load from the array, make a cons pair. So we'll always have either null or a cons pair on the top of the stack. So we start off with load null, get the length of array, store it as local. So we'll have load from the array, call this I. Make a cons pair, check if I is greater than the index, yeah. So we create a label basically. But because we're jumping back up, I think we can always know how far that's going to be. Right. So I'm going to take a short break. I'll be back in a minute. Right. So let's try and turn this bad collection of bullet points into some working code then. So the first thing we want to do is get the length of the array, which is this sequence here, where we load the array and load the length. We then want to store this in a local. So I think we can just do how do you add a parameter? How do you get a parameter in mono.cecil? Sorry, a local. You do store lock. Temp file. Where did temp go? New variable definition. Okay. Our body.variables to add. Okay. So we'll create a variable definition for this. And we don't want to create this variable for all the cases. We just want it for this. We only need it when we're actually unpacking a list. So we'll do it inside the unpack remainder. Let's just F-sharpify that. context. Assembly main module type system is going to be an int 32. What is that complaining about now? I think we've got the wrong number of parameters for the variable definition. I mean, we could just call it I like that. It's just expecting a type. So we create something called. So we can then store that. So if we store it in that variable, that's one thing. Right, it's actually two things. Then we load null. I can do that. Then does the emit return is the yeah, so we will create the loop target as a we want to load the null first. So the loop target is going to be the load from the array at index I. So loading from the array, you have the array, you load the index, and then you do a load element ref. So that's what this is going to be. So we load arg0, load constant, but in this case it's not going to be the constant. We're going to load the load lock I, because we want to load the index variable that we've been keeping track of. And we load the element. So now we have two things on the top of the stack. What we could kind of do with here is a constructor on the cons pair that takes two objects. So let's go and do that. So we create our current CUDA, we create the empty constructor. Let's call this create the cons constructor. So the cons constructor is going to be a bit like the empty constructor. Yeah, let's just copy and paste for the time being. Wondering how much of this code we can share between I think this is going to need to be is going to want to know these fields. So that's the car. Create cons constructor. Let's just get rid of that, to be honest. We don't need that. We can just add the constructor itself directly. So we create the constructor. At the moment this has got no parameters. So we will add 2 parameters. Parameter definition. We want an object and an object, basically. Yeah, we can do that. So we have a constructor that takes 2 arguments. It loads arg0, calls the base constructor, and then it does it'll load arg0 again, store, load the first argument, which for us is, I mean, I think this might want to be the CUDA. So if we load the, or we can load the second argument, and then at least the constructor parameters will be the logical way around. So let's load the first one. So and then store it in the our CUDA field. Store field, and then we will load the argument 2, store it in the because I think the second argument is going to be the most recent thing that we've put onto the stack, which is going to be the left value, the thing that we want to put, treat as the head of our current list. So it's a bit counterintuitive which way round that would go, but so we've got our constructor, hopefully. So we've got the cutter on the stack. We've pushed the argument at the next index onto the stack. We now need to actually emit a call to the new. We need to new object it, and the target in this case is going to be context.assembly. No, context.consttie get constructor. We just do 0 because we know that there is only one constructor. And context get constructor. Let's store this up here as well. Const constructor. Const constructor is a type object. Get constructor is an enumerable method definition. So if I can do seek.first on that rather than indexing into it. Let's do it this way around. So that should be, no, why is that not? I know, that's the other way around. Seek dot where's link when you want it? Sure, seek dot head. That'll do. Now that's a method definition. So we call the constructor, we leave that on the top of the stack. Then what we want to do is load the index again. Load the length of the array again, so that is index, and then branch if less than or equal to back. No. Branch if it's greater than. Just thinking about which way round we want to do the decrement. We can do the decrement here because I starts off as being the length, but we actually want one less than the length as our first index into the list. So this can just be branch if greater than. And we will branch up. We want to branch up to here. So the loop is going to be create an instruction for the same opcode and then add it. Then we can jump back up to this. So at this point, we should then fall through with the right element on the top of the stack, which will either have been a null or whatever. It's append, isn't it, not add. So what else did I say? And we want to store this back, but we want to first do thunk il dot Is there a decrement instruction? No. So we'll load one, sub it. We'll emit a duplicate instruction. So we've got one. So what we'll do there is we start off as I being length, and then we effectively decrement I, take a copy and store it back into I. So that's like pre-decrement, and then leave the original as the index that we use as the element reference. Right, it's going to be glorious if this works. Most likely going to end up with some unrelated error because I feel like that's been quite a bit of time before, quite a bit of time since I actually tried to run it. we call it we'll check the exception variables. Common language runtime detected an invalid program. And it was in thunk object 0, right. So I'm just trying to manually check here. That the stack is correctly balanced. So we are here, we load our load length, store. That seems fine. So what we'll do there is we'll then leave that load null and see whether or not that was, if this works, we can then slowly uncomment until we can work out where our IL is invalid. Well, it's not the IL that's invalid, it's my typing. Okay. It's still broken. Oh, we don't actually add the variable to the function. I think it's the body. Do we actually have to add it to? Yeah, it is. If this works, I'm just going to go for it and uncomment the whole lot and see how well it goes. I mean, it's a managed runtime. It's only so bad it can go. You get null. So it's not an invalid program. That's still going to be that null that we left there. So let's go and uncomment this. See if we get an invalid program this time. I think that stack should be balanced. No idea what this is going to show because there you go, we get a cons pair. But What is inside the cons pair? Well, we can put a breakpoint here. And find out. I'm just going to test the other code path, which is where we unpack the whole list. So the car is 1, the cutter is a cons pair, the car is 2, the cutter is should be 13 there. That's it. So argument passing and passing works. We don't have a nice way to print these cons pairs now, but I think that's a problem for another day. We're now correctly unpacking argument lists. So stage all that. Let's check over what the diff is. We've got our new type in the emit context to store the cons type. We've done a little bit of a refactor to use a with expression when we copy the context. Most of the work is here in unpack remainder, where we now loop through the remainder of the list and build up a cons list. We've got the error type that we load if there's an argument count mismatch. And I think that's it. Yep, that's good. And then we've got this add core decals, which defines the cons pair type. Let's put a quick comment there to say that's what it does. I can't edit it because it's not real. Used for representing at some point it would be nice for the compiler to for this to all be in a library and the compiler to support importing C# so that we could write things like the cons pair and stuff in C# and have it compiled down to and linked in. But for the time being that works, because what we're going to do is effectively every single time someone compiles a program, we'll recompile that cons pair type and just stick it on there. Variable right. Well, thanks for watching. That's just about the end of this stream, and I think we succeeded in finishing off Lambdas in the Feersum scheme compiler. So next up on my next stream, I will have to pick another topic. Got some parsing related stuff to do because there's lots of number literals and various other things, that object types that you can have in Scheme that the compiler doesn't currently recognize. So things like octal literals and hex literals and things like that. But we'll see where we go. Hope you enjoyed watching, and see you next time.